move on to our next presenter. Dear Buvaneswari and Senbaga Priya, are you here with us?
Good morning to one and all present here. I am Senbaga Priya, research scholar from the Department of Mathematics, Sri Krishna Arts and Science College, Tamil Nadu, India, doing my PhD under the guidance of Dr. R. Buvaneswari, Assistant Professor, Department of Mathematics, Sri Krishna Arts and Science College, India. And I'm here to present a topic on spectra of fuzzy graphs and graph operations in protein-protein interaction networks. So my abstract is based on the interactions on spectral fuzzy graphs includes vertex addition, edge deletion, contraction, perturbation, spectral variations under homomorphisms and various types of isomorphisms are explored. A key application is provided through protein-protein interaction networks in the context of systematic lupus erythematosus, demonstrating the utility of spectral fuzzy graph theory in modeling complex biological networks with fuzzy interactions. The relevance of spectral fuzzy graphs in capturing dynamics and structural evaluation under fuzzy transformations are also highlighted. A graph is a mathematical structure used to model relationship between objects consisting of vertices and edges. It is represented as G is equal to V, E, where V is a set of all vertices and E is a set of all edges. A fuzzy graph is an extension of classical graph E, and mu represents the fuzzy edge membership value of an edge between the vertices U and V. Fuzzy graph assigns membership values to both vertices and edges in closed interval 0, 1, which allows more realistic representation of relationships where the connections are not strictly binary. Spectral graph theory involves studying the properties of graph through its spectrum, that is a set of all eigenvalues of a matrix associated with a graph. The matrix may be either adjacency matrix, Laplacian matrix, and so on. Adjacency matrix represents the connection between vertices, whereas the Laplacian matrix is defined as L is equal to D minus A, where D is the degree matrix and A is its adjacency matrix. The eigenvalues of these matrices reveal structural properties of graphs. Von Collatz and Sinogowitz in 1957 posed the problem which characterized all non-singular graphs to describe the issue of nullity greater than 0. Later, Hoffman in 1968 introduced the spectral properties of graphs by examining the interplay between spectral and graphical properties of G. The seminal work of Dube in 1970 characterized graphs by the spectra, paved way for the pioneering work by Chivitok, Dube, and Sachs, and later in 1973, Feidler introduced algebraic connectivity of graphs, which represents the second smallest Laplacian matrix, quantifying the robustness of G. Lectures on spectral graph theory by Chung discussed basic facts about eigenvalues and stated simple upper and lower bounds on simple graphs. The introduction of fuzzy set theory by Zadeh in 1965 provided a way to handle uncertainty and partial information by assigning degrees of membership to elements. The application of fuzzy sets to graph theory led to the development of fuzzy graph theory, and the spectra of graphs resulting from various graph operations on products have been extensively studied, providing a foundation for understanding how different graph transformations affect their eigenvalues. The contribution by Anjali and Sunil Matthew on fuzzy graph energy and Venugopalam on fuzzy graph operations further enriched the field, making it applicable to diverse domains. Various operations such as contraction and domination have been studied to understand their impact on graph properties. A spectral fuzzy graph is a mathematical framework that extends spectral graph theory to fuzzy graphs, analyzing their structural properties using eigenvalues and eigenvectors of associated matrices. These are the preliminaries that is used for my study. I'll better skip this part. Fundamental definitions of spectral fuzzy graphs. Two fuzzy graphs G and G dash are said to be spectrally equivalent if their adjacency spectra are identical. That is, var gamma of G is equal to var gamma of G dash, where var gamma of G denotes the multiset of eigenvalues including algebraic multiplicities of A. A fuzzy perturbation operator. The G is equal to V sigma mu be a fuzzy graph with adjacency matrix A for a fixed tolerance level epsilon greater than 0. The fuzzy perturbation operator P epsilon is defined as P epsilon of A is equal to A plus E, where E is a fuzzy matrix satisfying norm E is less than epsilon. Two fuzzy graphs G and G dash are said to be spectrally isomorphic if there exists a unitary matrix U and a bijective mapping pi such that A dash is equal to U inverse AU and mu of ij is equal to mu dash of pi of I and pi of j for all I comma j belonging to V, where U and U dash are the fuzzy membership functions of G and G dash respectively. These are the theorems that we have developed based on the vertex addition, vertex deletion, and so here the bound modulus of var gamma I minus var gamma I of I dash is less than or equal to mu ij holds for all undirected fuzzy graphs due to the Wells inequality for complete and irregular fuzzy graphs where the structure is more uniform. And next we have obtained all these theorems for homomorphism, isomorphisms, weak isomorphisms as well. If two fuzzy graph G and G dash are isomorphic with adjacency matrices A and E dash, and their adjacency spectra are identical. So similarly, for any two isomorphic fuzzy graph G and G dash with Laplacian matrices L and L dash Laplacian spectrum is also equal. And now we'll be doing a practical application on protein-protein interaction network. So SLE is a complex autoimmune disorder characterized by the production of autoantibodies that attack the body's own tissues. So recent biomedical research has demonstrated that abnormal or dysregulated protein-protein interactions are implicated in the onset and progression of SLE. So here the authors investigated a research problem concerning SLE with neurological involvement, particularly focusing on the key proteins implicated in the disease effects on the brain. So to identify the most critical protein interactions, we have used two major protein-protein interaction databases. One is String and the next one is BioGrid, which provided comprehensive interaction scores based on experimental data, co-expression, and predictive algorithms. So while String originally are focused to set 14 major proteins that are recurrently linked to neuroinflammation and the cognitive dysfunction in SLE. So these are the proteins. And so with this, we have arrived at the fuzzy graph. So from this fuzzy graph, we are getting an adjacency matrix, and the corresponding Laplacian matrix is also founded. And the values are denoted here. So from this, spectral operations like vertex addition, edge deletion, perturbations are performed on this matrix, and the figure 2 tabulates gives the eigenvalues of fuzzy adjacency matrix under modifications. So these matrices were analyzed using Python for network modeling and eigenvalue computation, and MATLAB for additional spectral analysis and validated numerically as shown here in the table. Spectral properties of graphs with spectral radius, algebraic connectivity, and eigenvector centralities. These eigenvalues derived from the Laplacian matrix were then used to assess the structural and functional resilience of the SLE affected protein interaction network, enabling further interpretation of disease critical nodes. So for the original graph, the spectral radius is 1.7095, whereas after vertex addition, it was increased to 2.7763. Indicating a significant enhancements in the graph's connectivity due to the introduction of new protein with multiple connections following edge deletion between IL-6 and STAT4. The spectral radius dropped to 1.5587. So perturbation was also done here. And after perturbation, the top three eigenvector centralities are beta-2 glycoprotein, alpha-gluto, and HMGB1, indicating that perturbations could shift the influence of the proteins in the network is also obtained. So this is my conclusion. This work presents a novel framework for analyzing spectral changes in fuzzy graphs, focusing on operations such as vertex addition, edge deletion, perturbation, which modify the membership functions and spectral properties of graphs. Applied to SLE, the approach reveals new insights into disease progression by capturing uncertainty in protein interactions. Our research advances spectral fuzzy graph theory and provides a robust tool for exploring complex systems in uncertain environments with potential applications in biology, network resilience, and beyond. Future research includes extending the framework to dynamic networks and real-time biological systems. And these are the references. Thank you.
Can you able to find the same?
Yes, sir, because we are implementing in Python program. So once we are going with Python, n number of nodes can be done.
Then what about the complexity of your algorithm?
So I couldn't understand you.
Yeah, what? Because you wrote an algorithm and write a program in MATLAB, right?
Yeah, MATLAB is used only for the finding the eigenvalues and the computational values. Because
So what is it? Because you wrote some, you code some algorithm based on your algorithm, right?
Yeah.
What is the complexity of the algorithm? Can you increase the number of proteins or number of nodes more than 2 or something? Is it NP complete or NP hard? Because that is mandatory for proving your algorithm is better than the existing one. Okay, just think about
Okay,
that
sir.
way, then you write all those things.
Yeah, okay, sir. I'll
Yeah,
look into
okay.
that.
Okay, all the best.
Thank you, sir.
Thank you, Demi.